calculate the magnitude of the electric field, right, in between R1 and R2, right? Isn't that what it is? So I'll do it. I'll come here and say, okay, fine, this is my Gaussian surface. This is going to be the radius of my Gaussian surface. Is that good? And I say, okay, on the left side, I have what? Electric field times 4 pi r squared. This is the electric field going through the Gaussian surface. If you keep on looking at that, you won't get what I say here. Look at me. You know what I mean? You don't do this on your own. You're missing me. Miss a mí. Miss a mí. Miss a mí. That's what I said. Alhamdulillah. Right? Mesa.
That one is with the 7Q charge. It's gonna be with the 7Q charge.
This is a flux. Is the flux positive or negative?
Positive. The
Why?
charging side is positive.
Why?
The charging side is positive.
You got this side. I would say so. Because the charging side is positive, right? What am I concerned with right now? The amount of charge flow from my Gaussian surface, right? How much is it?
7Q.
And that's it. The electric field between R1 and R2 is equal to 7Q over 4 pi epsilon 0 1 over R squared. Simple enough? Hard? Questions? Questions? Questions?
Wait, how do you got a 1 over R squared? Is that a 1 over
4 pi epsilon 0 R squared.
Wait, how did you, why you have the 1 over R squared?
I separate the function. You see, I did it. Put the constant on the function. I did it there.
What? Is it also 1 over R over there?
Do you see 1 over R over there?
No. I don't understand though.
You don't see it now.
So the R is on top.
Maybe he got something.
Third dimension, fourth dimension. No, it's an off, it's clear.
17
Questions over here? You good? You? How about it? That's a nice one. Is that up? Yeah. How about it? You good? Over there? Pastor?
So the charge.
So, what I just did. Come on. You come late, leave everything behind, and pay attention to the class. Otherwise, you're going to be behind.
Why is
So you're going to finish the exam like a day after? Yes.
Why is the charge just 7?
You good?
Yes.
What?
Why is the charge just 7?
Why is the charge 7Q? What is the 7Q represent?
It's given to you.
It's a charge enclosed by the Gaussian surface, right? Is the whole sphere inside the Gaussian surface?
Yes.
What is the charge from the whole sphere? That's it. Got it? Good. Model? All right, let's do 4. Who wants to come to the wall and do 4 for me? No, you stay there. Jose. Go ahead. Show yourself. Chime.
It's RB and R3. Say that R
And lowercase r. That's lowercase r. 4 is lowercase r greater than r3. That means I'm looking for the field outside the arrangement, right? Isn't that what it is? Look at how long it takes me to tell them it's wrong. I love this. It's called I predict. By the way, check my stocks. Load JBool and also you cited or loaded the full text too. I didn't cite it. Is that what you're going to do in the exam? You're going to stare at the question for all this time? Is that what you're going to do this? You're going to like what, meditate when you're taking the exam?
Do we set up a ratio?
Yeah, that doesn't work. You know that, right?
You'll come to me.
Huh? Yeah, but it might take a while. I agree with you. It would come to you. You know, I value meditation as one of the most powerful things you can find in planet, but when you're restricted by time.
Fall asleep first.
Do we set up a ratio?
Excuse me?
Do we set up a ratio?
What ratio?
A ratio.
What for?
The charging
You
thing.
see, she says like, do we set up a ratio? What the hell is that?
Is it just 4 But R3 isn't a part of 4. Doesn't have the charge for.
Okay, let me see, Jose. Why are you doing that? Oh, because the professor did it, right? So I guess I have to do it too. What, you know what this shows, right?
Let me see the last question.
In your mind, you know how to use Gauss' law to solve problems. In mind, you have no clue about Gauss' law. Gauss' law. Zero.
I don't have anything.
Do you understand this? Remember, if you don't know, you don't know. If there is a hole in your process, you have no clue. Because there is only 2 parts to this expression. You see what I'm talking about? If you're missing one of the 2 parts, you're missing 50% of the knowledge. And I don't care how much you can rewrite whatever I write on the board. You see my point there, right? You should behave that way. You got it? Oh, I know there is a ratio, I have to do a ratio. Why? Because you're not asking yourself the proper question. And the proper question is, how much charge is inside my Gaussian surface? You don't have to do anything. Right? So I end up having 4Q over 4 pi epsilon 0 1 over r squared. Excuse me? Yeah, I leave it at that because I want to see that the 4Q is there. Later on you can cancel out and do whatever you want. You see what I'm talking about? But I want to see like what's the charge enclosed by the Gaussian surface. The 4 pi is because of symmetry. The epsilon 0 is because it's free space. And 1 over r squared is how ones depend on the other one. Right? What? What graph is that? Yeah, so it's what?
No,
Yo, this is the same. Question about this.
When you ask, for example, to find electric field on a certain distance outside the shell.
And in a specific distance,
Yeah, for example.
plug a plug.
Excuse me?
Plug a plug. Get that distance and plug it into your function. This is telling you the field anywhere
Outside.
outside. So you want to find a specific point, plug
Yeah,
it.
but for example, you put like that point is gonna have another charge.
No, that's to find the force on a different charge.
Ah, okay, so then you put it to Q and then you plug the distance.
You got it? So what she's saying is what a problem I did yesterday. And I said like, what would be the electric force exerted by this arrangement on a X amount of charge that I place a distance 2R3, for example.
So you have to find the charge.
No, you don't. I give you the charge.
Yeah, you get the charge.
Yeah, but it's
already.
like before.
You have the field, don't you?
Yeah, you give
What
us
you
the
do with
total
the field?
charge.
What do you do with the field to get the force? You multiply by the charge. Remember that? I told you that's gonna be the way it's gonna be, right? You find the field and then you find the force. The force is like a piece of cake. It's like 3-point question there that I give you just for fun. Got it? Wanna change the problem? Change the problem. Instead of telling you positive 7Q and
Negative 3Q.
negative Q, now I'm flipping that. Like flipper, yes, like flipper. Okay. So this is now negative 7Q, and this is positive, what was it? Before was negative, right? I need somebody to come to the board and chime. Carlos, to the board. So you're gonna see how Carlos is gonna do it wrong. Sometimes I'm afraid of challenging this guy. He'll be wrong sometimes.
That's me not good friend.
Huh? No, you're a great friend. You want your friend on the bus? It's up to you. Or a friend.
Same? Exactly the same?
Same problem. You guys complain. Sitting here is like nothing. Do one. Oh, part A, yeah. Let's go. Part A. Copy that. That's the real deal. You guys are next. You know I'm done with this one. I'll go now. Yeah, keep going.
Everything.
You're stuck when I tell you. Less than R? I didn't ask you that question.
R less than R?
Wait. No, no, no.
You gotta be careful.
That's the ultimate comes from the volume of
Good job. By the way, the capital Q lowercase q there doesn't matter. Is that clear? I know you meant the charge enclosed for the action circle. All pi R? That's bad. There you go. He's about to find the charge enclosed, but I got one, Maurice. No. I didn't change the materials, I just changed the charge. He's doing ratios. You do ratios when you have to. Is that clear to everybody? You don't have to do ratios. You don't have to do ratios. Yes, it is. Maria, mind your business. It will be nice. Once in a while, like, you know what I mean? Oh my God, what, Maria? What?
Oh, was it the, it only had a positive 3 charge?
It had 3 charges.
It had 3 charge and didn't have negative 7 charge?
No, I mean, for thought, the charge.
Professor, if the sphere,
I'm going to you in a second.
I just sounded like kind of different than the, not really with
It's always
part
gonna be
one.
negative. It's always gonna be
If the sphere and the shell were both negative, would it just be positive 7Q minus 10Q?
Yeah, I know that. I understand that.
Both negative?
Yeah.
No, you add the charge. You don't subtract charge. Okay, they are both negative, that will be negative 10Q. They are both negative. You mean for outside, right?
For the outside it would be minus 10Q and the inside would be positive
If the
7Q?
charge
Yeah, he did it
was
right.
maybe here, what
I know, I'm just saying like if they were both negative, right?
Oh,
Then it would
then
be
you-
positive 7Q inside, but outside would be something else.
Negative 10Q.
Exactly. Yes.
Oh, he did it wrong. I was like confused.
Okay, siéntate, Carlito. Is that all right?
No.
María, necesito que pongas un string in yourself. Is that right? He looks like he did everything perfect, right? True or false? And this is what happens to you people when you go to the exam and you do everything and you get a sign, ace this. And then it comes to the other. What was that? A magnitude has to be positive. It's so great. This is so great that somebody is realizing that the magnitude of a vector is always a positive number. How many of you didn't know that? You didn't know that? Yes, you did, Mauricio. Don't lie to me. Everybody knows that. Is that clear? The point is, it's not having a knowledge. It's being able to grab that knowledge when you need it. So what will you do then to fix that problem? Hold it. Go on there. Because you have that clear. At least you're aware of something is wrong. Fix the problem. Start the problem from scratch. Or fix whatever Carlos screwed up with right there. I told you this, you do something right or you do something wrong, right? There's no in between, like maybe right, maybe wrong. What? What the heck is that? Have you seen the absolute value in the Gauss law? Oh, let me change Gauss law and put an absolute value in, but you know, something gotta give.
It's dying? What is it on?
Sorry, Maria, that.
It was on 20% last time. It's on 10% now.
I mean, I guess I can't. There's no way to charge it. There's no way to charge it.
What happened? Oh, I cannot change the law. You gotta be a congressman to do it.
Jose.
Do you flip it?
Jose. Wait until this question is done, but yeah.
You can, right? You can do it? Delete it, put a finger in it. You think I will be able to spot it? I will be able to spot it. That doesn't work with me. I don't look at the final answer. The final answer is the least of my concern. It's the process. And that's me grading papers. I'll take my time, go under the tree, whatever I left in my house now, and go there and go sit down. And I'm going to show you that, by the way, I'm using this, and don't get me, it's not personal, it's business. that he doesn't know Gauss law. It's kind of hurt, right? Right? Sit and let me explain the problem. I told you the Gauss law is a 50-50. You work on the left side and you work on the right side. It seems to me that Carlos was right on the right side. All this, Carlos, you will get on the point. Don't delete this just because. I'll look at it.
The next one then.
What?
That's 7.
You cannot delete it. You know what the problem is? He had no problem with the charge enclosed by the Gaussian surface. He got a problem with the flux.
The flux is negative.
Negative flux.
Is a negative charge.
You see the point, right? And now you're like, I know this Gauss law stuff. And that's what I did. Because if everything is you're lucky, everything goes like smooth. You see what I'm talking about? Now what if you're not lucky? What if your professor designs the problem so that you have to take that into consideration? It's not because I'm out there to get you. It's like my goal is, what is the problem, the purpose of an assessment? What is the objective that you have to show me that you manage? The students should be able to use Gauss law to solve problems involving continuous distribution of charge with highly symmetrical situations, cylinders and spheres. It's simple. I keep it simple. And why I insist on this so much? Because this is actually how you actually learn something. You cannot have flaws on it. Everything is important. Is that clear to everybody? Will you ever see Gauss law again in your life?
No.
Never. But if you're a good engineer, this is going to help you a lot. Go ahead.
The number 4 that I tried to do, the electric flow, the float is negative too, because we were working with minus.
In your case, see what I do to you. I'm grading this. That's the way you will see it. You missed the dot. No, you got it right. You missed the dot. Thank you, Nes. Go ahead, Jonai.
So I don't understand what's the total, like I don't understand the charges, because the -7.
The charge is fine.
Okay,
You
but
have
can
no
you
issue
explain
with the
it to
charge.
me?
That will give you 3 points. The
But-
flux on the left side will be 2 points. Right?
Okay, yes.
Now, this is the key. He picked this Gaussian surface, right? In what direction is the Gaussian surface? Going outside. That's the convention, right? Right? We say that whenever a surface is closed, the direction is outward. The charge enclosed by the Gaussian surface is positive or negative?
Negative.
So in what direction should be the field created by the charge enclosed by the Gaussian surface? And what's the angle between the charge and
Pi.
pi, 180, whatever you want to say? Is that clear to everybody? So the dot product between the field and the area at every point is negative.
Negative, because cosine pi is negative.
There you go. And now everything makes sense. True or false? You don't have to break the law by putting an absolute value here. You delete it. You know what? You think I don't notice that? I look at this. If there is no negative sign there, I take 2 points away from you. You got 2 out of 5.
But better than leave everything here.
I don't know. Do whatever you want. Well, it would be nice you learned Gauss law. That's it.
Yeah.
The key is it's not more like, oh, I do this, I do that. Or I know I have to do a ratio. And you do, no. Look at the problem you have in front of you. Who wants to go up and do the last one? The last part. Part 4. And Jonai?
I'm confused about the charges.
And Jonai, I spent 2 classes
I
explaining
know,
this.
but
I'm not going to spend another class with that. Who wants to do over here? Huh? Oh, yes, Jessica. Dale, casi lo puedo utilizar aquí. Desde que empezaste con Hurry up. Hurry up. Do the last one. Come on, Jesse. Up we go. 1, 2, 3, up. Go ahead. This is probably the first time in her life she's going to the board. Shine, Jessica, shine. Rafael?
You write it down?
Christy?
No, I'll give it to you.
Axel? Part 4. Emily?
Here.
Stefano? Stefano? Andres? Natalie?
Here.
Stefan? Michael? Who's Michael? Anthony? Anthony? Giordano?
Give me 7. Oh, this is negative 7. 3. So you have to find the chart. Basically, I guess you have to draw the button. So he wants to know what's the charge on that.
Good. Go. Sit down. Is the answer right? The answer is right. Yes, it is. The answer is right. The process is wrong. This is great. That's the magnitude of the electric field, right? At a distance r greater than r3. The process is wrong. The answer is the last thing I look at. See what I mean? And usually on the answer you miss points, like 0.5 point if you made a mathematical calculation, a silly one. It's damaging when you put the dependency wrong. That's like 1 point, 1 whole point. You see what I mean? But, first of all, the charge is not 3, it's negative 3. Or negative 4, even worse. It's negative 4. But I don't even look at the 4. I look at it's negative. So you know what this is? Minus 1 point. Right? Also, the flux is negative minus 1 point. And why did you lose 2 points if you know what you've been doing? I just explained this a second ago, right? Right? The rest you will be able to do. Got it? So don't waste point for nothing, people. Don't think that you know how to solve problems using Gauss' law. If you don't know Gauss' law, you won't be able to do it. You got it? And simple problem like this will lead you to screw up in that sense. And 1 point at a time, you lose many. Questions? This class, because of your mentality, gets better as you move towards the end. So believe it. True. As you get towards the end, it becomes easier. And it's not because the content is easier. The content is a lot more difficult as you move on. It's because of what? Anybody know? Because you finally accept reality. You accept that if I don't know, I don't know. You got an idea there? And that's what I do. That's what I take my time. I take my time. at the beginning, with the hope that you will follow. Monday, I told you the exam for this class is when?
Wednesday.
I'm moving into Monday of the following week. The reason is I'm not coming on Monday. You got the deal?
So,
Yeah, I have to stay with my daughter. It's like a teacher practice.
For the final answer, right? It's
Good.
it's supposed to be 1 over r squared.
Oh, no, the way you put it doesn't matter. Because I want to, I have like bad habits. I like to leave always the constant and the dependency. You see what I mean? Whatever is a constant, that is a dependency, because if I'm being asked to plot, I will make sure this is plotted according to how the field depends on distance.
Professor, if the shell was a non-conductor,
Then it will be a little more tedious.
then we should like add the charge of the sphere and the portion, right?
Okay, let's do this now. Usually I don't put this in the exam. I might, by the way. It depends on how I feel the day before. But let's change the problem. I say here solid non-conducting. See how tedious this is. You got it? So the first part remains the same. Is that clear? The second part remains the same. The problem is that now you have charge inside. Now you have electric field inside this thing. Now part A doesn't change. You got my idea there? Part I changes, because since this is a non-conducting object,
Will be always
the 3Q will be all over and it will not be affected by the presence of this. If you ignore polarization effect. You got my idea there?
yeah.
So you will have an evenly distributed 7Q or negative 7Q. What do you want to be, negative or positive? Let's leave it negative, because that's where you guys have the problem, right?
So, it's not like the inner shell or the outer shell is gonna be a different charge. It's gonna be the same.
If I give you something like this, I don't ask you that question.
Okay.
You got it?
Yep.
So why? Because the charge doesn't rearrange in a non-conducting object. Make sense? So everything has to make sense. So here, same thing as before. Here, same thing as before. Is it right? Here is the problem. So what I'm going to do, I'm going to draw my best Gaussian surface. Right? What is my best Gaussian surface? An spherical surface with radius r in between R2 and R3. Is that right? Let me work the left side of the equation. You got it? And here it is, this is crooked now. What's the left side of the equation? I'm gonna say, is this term positive or negative? Or negative. You have negative 7Q plus something less than 3Q. You guys got the deal there? You got it? Negative 7 plus something less than 3 is gonna be negative still. So the key point is, like, the charge enclosed by my Gaussian surface, all is negative. You got it? So there will be a negative flux. Is that clear? So I'm assuming it's negative. This is equal to epsilon z. Now I'm going to start with what? Negative 7Q. Up. Right? Because I know I have negative 7Q inside to begin with. Does that make sense to you? Which is the charge contained on the inner sphere. Now I have to find the charge contained, let me show you, in this volume here. Is that right? And this is when I say be creative. Be MDC. Right? Are you guys getting my idea here? So you have to be creative about that. Do you have to do ratios now, Eljon? You have to. It's not you have a choice. You see what I mean? And see the ratio.
We have to do the ratios in brackets to be a positive?
No. You have to do the ratios when the amount of charge you're trying to get is less than the total charge. The ratio is because the charge is even distributed, right? Has nothing to do with positive and negative order. So here we go. Remember, I'm going to add something, right? Let's put that question mark in here. So what is question mark?
It's another cube, small.
A certain amount of cube, certain amount of charge contained here. And this is the way I'm going to do it. All the charge contained on that shell is to the volume of the shell. Do you know the volume of the shell?
It's F2, F3 minus F2.
4/3 pi r.
What are you going to write down here?
It's gonna be
4/3
pi
pi
R
R3
R3 minus
R2.
R2 square.
R3 to cube. For cube.
Q minus
No,
No,
F3
equals.
F3 minus
Four
F2
P.
cube. Everything
Yeah.
cube.
minus 4B R sub 2 Q.
Same thing. Just
Over
put the
three.
bottom.
It's true. You got in the sphere, you remove part of it, you're removing. It's a difference, right? You got the whole volume minus the empty space inside. Right? Some of you might say like 4/3 pi R3 to the third minus, you know, because factors out. Is that clear? So this represents the volume of this whole shell. You got it? The shell goes from here to here. You can use the shell method and integrate, and you might be able to get it too. Yeah, you might remember the A you get in that part of your class. So that question mark, which is the chart I'm looking for, is over what?
The volume of the shell.
Over? Any idea? No idea? Go on. One?
The volume of the shell. The volume of the shell
Plus-
in the
plus
enclosed by the Gaussian surface.
Yes.
With
Excuse me.
just with R, with lowercase r.
Excuse me. Hurry up.
4/3 pi r cubed.
There's a bunch of R's in here.
Lowercase r cubed.
Is that it?
Minus 4/3 pi R2 cube.
If you leave it like this,
Yeah.
you're telling me that there is charge all the way through, from 0 to that point. You have to subtract the part you're not considering. Right? Right? As usual, this 4/3 pi, whatever, is specific to spheres. And I have that question mark is 3 cubed, alright? Times R3 to the third minus R2 to the third. The whole thing divided by R to the third minus R2 to the third. And then I put this in here. What's this? 3 cubed R3 to the third minus R2 to the third. How many of you are like, oh my God, why I decided to become an engineer? R to the third minus R2 to the third. Right? Makes sense? And you probably solved.
Isn't it flipped?
Did I screw up? Yes.
The-
Right.
R3
R-
has to be
Yeah, absolutely. Don't make that mistake in this.
Yeah, R small is in the other side as well.
R3, right? Obviously, like this, I don't have a way to say whether I screwed up or not. But when I simplify, I see the dependency. So you divide the whole thing by 4 pi r squared. Let me show you.
Wait, no. No.
Why are you gonna do this, Maria? Let me show you how this field stays all the way to the end. The electric field is equal to, I'm going to divide the top by that, everywhere. Is that clear? So the first thing I have is 7q over 4 pi epsilon 0, 1 over r squared. Okay? Minus. See what I'm going to do? 3q, right? Over 4 pi epsilon 0 r 3 to the third times r. Isn't it? Trying to be good at math, which is difficult. Then I have plus, okay, 3q r2 to the third, isn't it?
Negative.
I forgot to put in here like all this, right? Let's put this properly here. This is like r3 to the third minus r2 to the third. Is that right? And don't forget the 4 pi. Yes. 4 pi epsilon 0 r3 to the third minus r2 to the third. Right? Let's look at this. 3q r2 to the third, isn't it? Over 4 pi epsilon 0 r3 to the third minus r2 to the third 1 over, is that right? R squared. These are the expressions. You see what I mean? Now, if you analyze this properly, you're going to notice that this term refers to the inner sphere. The contribution of the electric field coming from the inner sphere. You see what I'm talking about? The field will decrease with distance away from the inner field, regardless of what is in the middle. You got it? That's the first dependency. These two terms is because of it's a shell. You see what I'm talking about? Now, notice that this is a contribution of the shell with the field increasing. You see what I mean? Because you are storing more charge. That's why you have a linear relationship, as you have before with the speed on part 1. You see what I mean? And this one is outside that shell. It's a combination of two. You see what I'm talking about? So that outer shell actually affects this in 2 ways. You see what I'm talking about? The outer shell affects it in 2 ways. More charge and more distance. Anyways. So you see how complex this is? Obviously in an exam you don't have to do all this. You give me the final answer, you divide by 4 pi r squared and I take. I don't want to waste time on the simplification and stuff. You simplify when the simplification is obvious. You got it?
I got those why you minus instead of plus.
What?
At the beginning it was like plus.
Yeah, but remember the flux was negative.
Ah, okay.
So I deleted it. So what would be the electric field on the surface of the outer shell? On the surface. Right on the surface. You might be able to use this, right? Isn't it? And you will replace this by R3, right? R3 minus R3.
Easy is the addition of all of them, no? And the
You
other
got
one.
an determination. You cannot put a 0 on the bottom. No, hold on. There was a 2 minus Q over what?
So you put in 0 to
4
the
pi epsilon 0 r what?
3
3 squared to the third minus r 2 to the third, right?
Yeah.
Now this is what you place as r3. Is that right? You got it? On this one, you place it here. And that's an ugly expression, which is a number. So if I ask you for the field at certain specific point, just plug a number. Got it? What?
You can do it also adding everything,
How do you want it?
like the electric field inside the sphere, outside the sphere,
No.
inside the shell, and that will be the total.
No, because this is a continuous distribution. It's a different story. You use Gauss law. That's the nice thing about this business, isn't it? So you guys are ready to ace that question on the exam? The Gauss law question?
Yeah.
When you gonna be ready? The day before the exam? Bad news. You won't. You're taking too long. How long have you been doing Gauss law? 3 days. 3 days. Came with flux and I saw point form and look at this. Today I told you 20 minutes, right? And look how much you've been doing it. Anyways, let's move on.
Are you gonna sketch the
No, that one I can't sketch.
not that one,
Stop.
no, this one, the first one?
The field is going to be either like linear, 0, or it's going to be 1 over r squared, like that. But you can put it in your calculator. Remember, that's the reason why I separate the constant from the r, so I see dependency. Obviously, I don't give you complicated stuff where you have to waste a lot of time calculating ratios and stuff like that. And if I do, I make the other side simpler. I do all that. Because whether you like it or not, you have to finish the exam in an hour and 40 minutes. You see what I'm talking about? I do all that, but the key is you have to be ready for that exam. You're waiting until next week to be ready, it's going to be too late. Questions? Anyways, up to now, we have seen what I call in physics 1 the force method. In physics 1, when I teach a class, I break the course in 3 things, in 3 parts. You see it? And usually the exam shows the end of the part. So when I teach, I say, okay, the first exam is going to cover kinematics and forces. And you apply Newton's law and whatever. And usually everybody does the same thing, by the way. So it's what I call the force method of solving problems. See what I mean? Then the second exam, if you probably recall what was the second exam, you may,
Energy?
it was all about energy, right? Remember that? And I call that the energy method, which is easier than the force method. You learn some other concepts and you solve problems. And then you apply those two. In mechanics, you apply that to rotational motion, in which you define torque as part of the force method, and you define rotational energy as part of the energy method. Remember that? And then at the end, you have a bunch of stuff like simple harmonic motion, gravitation, fluid mechanics. So it's applications of the mechanics to different specific situations. In here, we do the same thing. You see what I mean? And we do it for electricity and for magnetism. So all this comes from the property of matter, which is called charge, right? And we define the interaction, the electrical interaction, in other words, Coulomb's law, through holes. And then to make our lives easier, we come out with another concept. What concept was that? What's that? No, Gauss law is a law. Flux is a mathematical thing. Electric field. You see what I mean? The purpose of defining electric field is to make our life a lot easier. You see what I'm talking about? Because calculating the force, you needed 2 objects interacting. But you know the field at a certain point and you put a charge there, you know the force, right? So essentially, the force method is all about this. Obviously, in the process, you learn how to do stuff, right? Like Gauss law is a nice and beautiful way to do electric field. You know what I mean? And yeah, I have a point like charge how do you calculate the field at a certain point, blah, 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 blah. But at the end, this is all. You see it? But you were exposed to the electrostatic interaction. That's it. The rest is a bunch of derivatives. So, what I'm going to do now, I'm going to introduce the concept of electric potential energy. Today's 9/27/2017. Electric potential energy. I am going to introduce the concept of electric potential. And that's all you need. The rest is a bunch of little details. Is that clear to everybody? You have to make a distinction between these two. So the way I put this in my head, you know, in my physics brain, whatever it is like, oh, this is equivalent to the concept of force. And this is equivalent to the concept of electric field. You see what I'm talking about? So the purpose for me to define this quantity here is because it's useful. It makes our life a lot easier. Is this clear to everybody? So let me go back to your mechanics. In mechanics, you define work, the work done by a force. All right? As what? Well, that depends on the situation, but I'm going to make it general. In general, a force does work in an object when it moves the object certain displacement, right? That was your definition of work. And I hope you understand that there is a dot in here that you cannot ignore. See, when I teach this, I go over this more than anything else. As you see here, you know, so people have an idea. You know, force times this is what it is. It's only true when the force is constant, isn't it? Isn't it? So that was the definition of the work done by the force as the object moved from location S1 to location S2. Is this clear to everybody? So essentially, you have the force, you multiply it using the dot product but in a small displacement, and you add that product. You got a number, scalar, which is work. Is that clear? The uniform work was
Joule.
Joule. You see it? And Newton's third law was converted into energy. You see what I mean? By means of the work energy theorem. So instead of speaking about the force acting on an object, I speak about the work done on the object. What work am I talking about? The work done by the net force, or network. Is that clear? What that thing is going to do? Well, it's going to alter the state of motion of the object. So it's going to change the kinetic energy of the object. You see it? And the kinetic energy of the object is the energy the object has because it's moving. It's related to the speed of the object, and it's related to the mass of the object. Do you remember this? This is a review, a little refresher. Is that clear to everybody? Then we define another form of energy. You see it? A form of energy that has to do with position, not with motion. Like for example, when you have a spring, you stretch it, that system, a spring hand system or a spring block system, whatever, is going to get more energy, and we call that energy what?
Conservative.
Hold it, we call it elastic potential energy. Is that clear to everybody? The reason you call it potential is because the more you stretch that spring, the greater the potential for that block to go back. Is that clear? We extended this to lifting an object. So if you lift an object a certain distance from the ground, not a long distance, certain distance, then that object will gain an amount of energy that has to do with gravity. And we call it what? Gravitational potential energy. All these are not kinetics, so they are what? Potential. Why potential? Because that depends on position. The more you lift it, the greater the potential. True or false? You see it? But that was a fluke. When you found the potential energy of an object that you move a distance h above the ground, you see what I mean? You say, the potential energy is mgh, and that's messed up. It's messed up because you're assuming this doesn't change after you lift the object. So that was an approximation, a gross approximation. And towards the end of the semester, depending who you took it with, you were exposed to something called gravitation. And you finally spoke about gravity as something real. So, if you have an object at a distance RE from the center of the Earth, you see it? And you move the object a distance h from the center of the Earth, the force of gravity between those two objects, mass of the Earth, mass of the object over r, changes with distance. This is an approximation. You're assuming that you're not moving that much. You see what I'm talking about? So this is significant with this, so you assume this is constant. But this is the real deal. And you define gravitational potential energy, and the formula came out to be whenever two objects m1 and m2 are separated by the distance r, there will be an stored potential energy on that system, the system of the two objects, that is proportional to the product of the masses and inversely proportional to the distance between the masses. Is that clear, everybody? The more you separate two objects, the more the potential. So when you speak about lifting an object from the ground, it means separating that object from the ground.
It's less.
Excuse me?
More is the bottom, it will be less, no?
Great. It's nothing new. Don't you have to do work to separate them?
No, I'm thinking about that position.
What do you mean?
No, it's because if you have R there on the bottom, or R bigger, it will be less.
Energy is a scalar. And the smaller the scalar is greater than the negative of it. You see my point, right? That's key. It's like energy is not a vector. So that's the nice thing about this business. You get away with vectors. Forget about it. You see what I mean? So what I'm going to do, let's speak about 2 point-like charges. Shall we? So let's say I have a charge here, and this charge is Q1. At a distance R1 from Q1, I'm going to put a charge Q2. For the purpose of simplicity, let's say this charge is a test charge with the amount of charge Q0. Is that clear? So, the question is, what will be the charge stored by this, the energy stored by this system? What type of energy would that be?
Potential.
It would be potential, right? What potential? No, that's no point.
You lose some strength
Is it-
with distance.
There's an R there.
Maybe.
And it depends on position.
How do you know it depends on position?
Because there's that R.
Let's find it. Let's find the amount of work an agent have to do to move this charge from this location to this one. Shall we? So let's say Q naught is being displaced from point A to point B. Where point A is at a distance R1 from this charge, our point B is at a distance R2. So let's calculate the amount of work done by that. Shall we? I'm gonna calculate the work, and obviously I'm gonna do it little by little. Is that right? So if I push it, isn't it? And I multiply by the displacement, I'm gonna say dr in this case, because it's a radial thing, isn't it? Then that will give me a small amount of work done, right? In order to move in a small distance, it doesn't matter how strong the force is, right? If you move in a small distance, the amount of work you have to do for that is what?
Very small.
Very small. So if you're gonna move it a longer distance, that means you add all the little work, right? So you got the work done by, what force are you talking about? Well, let's assume that you are pushing it so that the object doesn't get kinetic energy. But you don't have to worry about the kinetic energy. The object only gets potential energy. Is that clear? So, what is that equal to? What force is this one? Of the electric kind, right? And I guess you know the nature of that force, right? I'm going to go back to K. K, Q1, Q0, over what? R squared, R, dr from it's another way you calculate the work done by the force. You have to integrate because the force changes with distance. Simple enough? So I believe you can do this in a flash, right? Now, what's up with the sign of this?
If it's pushing it away, they have same sign.
That depends.
Yeah, because the negative is always positive.
The testing
Because,
charge
that-
is always positive, no?
Same sign, they will be always positive.
This is very difficult because there are too many variables in this business. You know what I mean? If this is negative, remember you're going from here to here. The dr is in this direction. You see what I'm talking about?
Yes.
But the force is going to be what? Either this way or this way. You see my point? And this is a dot product. So this is going to come out positive or negative based on what?
And the angle.
On whether
The charge is
the charges are the same, are equal, or whether you're bringing the charges closer or you're separating the charges. This is crazy.
No, but in that case, since it's moving, that side means they are going far, but the charges, they have the same sign. It's
Well, who
always
told you
positive.
the charge have the same sign? What if they don't have the same charge sign? So you have like 8 different possibilities
No,
in this.
in that case, it would go this side because it's going too close, because it's attracting it. But now it's going farther. Means they are-
But what if the charges are both positive? What if the charges are both negative? What if one is positive and one is negative? You see my point, right? What if you're moving away, separating the charges, or you're bringing the charges together? So it's too much to get in one head, isn't it? Especially if your heads are full of information. So we don't go crazy about this. You think in your head, okay? And we say this. Let's say they have 2 positive charges. What would they do? Repel each other. So it doesn't take any work to separate them, right? The work you need to do is to bring them together. Isn't it? And the opposite will be when the signs are different. Like for example, how many of you have taken chemistry already? At least the first chemistry. Anybody have taken chemistry, right? At least some sort of chemistry. And remember ionization energy? Anybody remember that? Mauricio, do you remember anything in school? Like, ionization energy was defined in chemistry as the amount of energy you have to give to an electron in the valence layer to remove it. Or the amount of energy you have to give to an electron to push it into the valence layer of the atom. Remember that? Maybe you don't even know what it means, valence layer. Remember that? But my point is like the nucleus of any atom is what? Is it neutral? The heck is that? That's probably nirvana. But the nucleus of atoms so far are positive. Right? You got my idea there? And electrons on the periphery are negative. You see what I mean? So ionization what? You have to provide energy, like by means of heat, electrical energy, whatever you call it, so that electron is pushed away, pushed away, pushed away, and how far you have to put it so it doesn't interact with this nucleus anymore, in theory. At infinity. Is that clear? Are you guys getting my idea here? And then the valence layer is actually the opposite. The valence layer is a bunch of electrons. The more electrons you have in the valence layer, the easier it is for you to ionize. Do you see why, right? They want to push each other apart. So you don't have to give them that much for them to go away. Well, this is the principle of conductors, isn't it? So it's the interaction of the electrons of the valence layer and the interaction of the electron with the nucleus. What makes this distinction? Is that clear to everybody? So they are opposite type of interaction. An attraction, nucleus and electrons, and a repulsion, electrons and electrons. Is that clear to everybody? So you have to treat it differently. In fact, when you calculate the ionization energy of, for example, hydrogen, that's the simplest one, right? Anybody know how much energy you have to provide to the hydrogen atom to ionize it? Can you share anything you learned in your chemistry class with me? Anything? Significant figure, right? It's 13.6 electron volts. Have you heard about that before?
No.
1 electron volt is equal to 1.6 times 10 to the negative 19 joules. It's a very small amount of energy. Obviously, you have a lot of hydrogen atoms. They are up. Anyways, let's keep on working on this because mentioning chemistry is a nightmare to you. So let's take the constants out. I am going to ignore the charge for now. Got it? So the constant out, I take this K, this Q1, this Q2. What else I take in here? And I integrate what? Oh, by the way, this and this will depend, right? So for example, you have two positive charges, then the force will be a repulsion, right? Which means R and dr go in the same direction. Does that make sense to you? Mauricio, that's the reason why you didn't learn anything in chemistry. And you won't learn anything in physics either. You keep on. The difference is you will be able to pass chemistry not learning anything. But with physics, it's going to be quite difficult. Anyways, so I have in here what? dr over R from what? R1 to R2. Is that right? Do you know how to integrate this? Oh, do you know how to integrate this?
Minus 1 R.
Mauricio, mathematics?
It's negative 1 over
Oh,
R. It's negative 1 over R.
yes, it's negative K, Q1, Q naught. As a matter of fact, I didn't call it Q2, I call it Q naught.
Over R.
Divided over what?
R.
R. Right? From
From
R1 to R2. Is that right?
It's not R squared. R3.
I'll move on. This is equal to
No, sorry.
K, Q1, Q naught over 1 over, I'm going to flip this, right? R1 minus 1 over R2. What is this? This is the amount of work you need to do to separate two objects certain distance. For now, I'm assuming the two objects are positively charged. Is that clear to everybody? If one is positive, the other one is negative, you will have a negative sign here. Is that clear to everybody? Now, let's speak about the electric force. If you take this object from here to here, but following this path, how much work you will have to do? Instead of going straight, you go follow the path.
Same.
The same. Is that clear? Because
Doesn't depend
the
on
force is radial. Any perpendicular component of that force will not do any work. So what matters is the amount of work you do on that line. Is that right? Is that clear? What if you come back? What is the work done in going around and coming back to the same point? Zero. So believe it or not, you actually define what is a conservative force. A force is said to be conservative when the work done by that force across a closed path is zero. And electric forces as well as gravitational forces are conservative forces. I know this is the boring part of this, right? But you see what happened afterwards, right? And I don't have time. You have an exam next week, Monday, right? So get this, otherwise it's going to happen the same thing it happened to you when you did the Gauss law that you thought you knew. What I have found in here, the amount of potential energy that this system acquires when you're separating that distance. You do the work, and that work that you do becomes what? Potential energy. So you calculated the potential energy stored by the system when you separate the charges, that distance. That potential energy is going to be positive or it's going to be negative, depending on whether you bring it together, separating, and also the sign of the chart have to be taken into consideration. Go ahead, Jose.
No, nothing.
Good. Questions about this? Questions about this? Now let me introduce this, and I hope you start paying attention now. You haven't paid attention yet. Let's say I have a positive charge Q1 here and a positive charge Q2 here, right? This is what you call a system. Is this clear to everybody? Let's say these two charges are separated by a distance r. You got it? What would they tend to do? Repel each other. Is that clear to everybody? Does it take any effort to separate them? No. Does it take any effort to put them in this way?
Yes, yes.
At that distance? And that would depend what? It will depend on the charges and the distance between them, right? Is this clear to everybody? So, organizing a system, like you as a human being, okay, there was a bunch of atoms and molecules and electrons and whatever, and somehow all that came together. You see what I'm talking about? In chemistry, they call that binding energy. Remember that? Binding energy? The energy required to break something?
Oh, yes.
Well, that was the energy employed to put it together. Does that make sense to you? You didn't get that in chemistry yet? Anyways, and I'm talking about the common concepts, not the complicated one that gives energy. Wonderful. What was that? Anyway, let's move on. Hopefully, yeah. So, it is like bringing Q2, for example, from infinity, isn't it? At infinity, there is no interaction between Q1 and Q2. So, if you calculate the difference on the amount of energy you have to provide to the system to bring this from infinity to this point, you found the energy stored by the system. In other words, in here, you will put this at infinity. You see what I'm talking about? This is what? Zero. And you found the energy stored by a system. I'm gonna U, just like that. Obviously, I'm assuming U at infinity is zero. So U is what? K, Q1, Q2 over what? Over R. Now, this now is a lot simpler than before. You got it? Because the only have to worry about is just to put the proper sign. You got my idea there? If Q1 is positive, it would be, and Q2 is positive, this energy will be positive, meaning you have to spend effort bringing it from infinity. If Q1 and Q2 are negative, the energy will be positive. It means that it will require energy to bring it together. But if one is positive and the other one is negative, this will be negative, means it doesn't require energy to bring it together, but energy to separate it. Is that clear to everybody? And that's the reason why the ionization energy of hydrogen is negative 113.6 electron volt. Is there any question on this?
And the units will be joules as well.
Absolutely. The unit for electric potential energy is joules. Is this simple enough? I got 55 seconds. Questions? You know what? Questions about, so I'm going to leave you with a simple question. I got a system arranged in this fashion. 4 charges, Q1, Q2, Q3, and Q4, okay? All of them are the same, except for the fact that 2 of them are positive and 2 of them are negative. Yeah, the distance between this and this, D, between this and this, D, between this and this, D. I need to find the energy stored by this system, the electric potential energy of that system. How will you do that? Time's up. I'll see you on Wednesday. Remember, those of you that came late, there is no class on Monday. Junie.